Welcome to the third video on the D block chemistry, and this time we're going to be looking at oxidation states. Now we're going to spend a whole video looking at the oxidation states of D block compounds and their trends and why certain ones are present with certain elements and not. And this is because, as I've been saying throughout, the oxidation states and cations are like key to all of the transition metal chemistry. So let's start by looking at what oxidation states are possible. So here I've got a table showing all the oxidation states of the first row of the D block, and you can see that there are absolutely loads possible. So with the exception of scandium at the very beginning and zinc at the very end, all of the elements have several stable oxidation states. When we look at manganese, you can see there's absolutely loads. So the ones highlighted in green are the most common ones, and it means we can quite easily make compounds with all of these. The red ones, these are so like around 0 or negative, the lower oxidation states. They're not stable in aqueous solutions, not with water, but they'll be stabilized by ligands such as CO. And we'll come and talk about ligands and their stabilizing effects in a few videos' time. The higher oxidation states, the ones in grey especially here, aren't very common, and this is just because they're extremely strong oxidizing agents. And that's because these elements don't want to be in such a high oxidation state, so they want to gain an electron, they want to be reduced themselves and in turn oxidize something else. I've already highlighted manganese and how it's got so many oxidation states, so it has 11. And its maximum oxidation state is +7. You can see from this green diagonal line here that from scandium all the way over to manganese, the maximum oxidation state is possible. They're highlighted in green, they're actually pretty common. And this occurs with the loss of all the 3d and 4s electrons. So they've got the same noble gas configuration as argon. They've got no 3d electrons at all. Now, as we go up from scandium to manganese in their maximum oxidation states, these become more and more oxidizing, and this is because they're in a higher oxidation state. And the top ones, so especially permanganate, or the permanganate anion as shown here, is a very strong oxidizing agent. And as I've said before, oxidation is I'll do this oil rig thing. Oxidation is a loss of electron, and reduction is a gain in electron. So when things like this permanganate anion are acting as powerful oxidizing agents, they themselves are reduced in the process. And at the top here I've got an example of this permanganate anion performing an oxidation reaction on an organic alkene. So you can either add 2 alcohol groups to it or break them down into 2 ketones. But you'll learn more about alcohols and ketones in the organic chemistry part of the course. So what other trends have we got in the oxidation states? Well, the maximum oxidation state is very stable and common up until manganese, but then after manganese, so iron, cobalt, nickel and copper, the maximum oxidation state is really rare. As I said, their compounds are really strong oxidizing agents because they don't like to be in such a high oxidation state. They want to be reduced. At the beginning, we can see that the common oxidation state is +3. +2 is possible, but not that common. Although where we get to the right-hand side, the group or the row, the period or the row, sorry, the +2 oxidation state becomes more common. There's a bit in the middle where +3 and +2 are both really common, but from nickel onwards, +3 is rare and unstable, and +2 is what's common. And the reason for this is down to the ionisation energies. So I said in the last video I'd come back to the ionisation energies because they're so closely linked to the oxidation states. And here we are. So for a quick and obvious recap, to get to the +2 oxidation state, we've got to lose 2 electrons, so perform the first 2 ionisations. And to get to the +3 oxidation state, we've got to lose 3 electrons and therefore perform the third ionisation. Now the third ionisation energy, therefore, is the one we're really interested in. And this increases across the series, as we've seen. It's got this anomaly between manganese and iron due to the paired electron, if you remember. But then, if we're going higher and higher in ionisation energy, it gets to a point where it's just too high. So that point's here, nickel, where we saw that the +2 oxidation state is the common one and +3 is unstable. And that's just because this third ionisation energy, the one that's required to get it to the +3 oxidation state, is too high and it's less favourable to form that +3 oxidation state. Now, when we were looking at the S block and the P block, we looked at the oxides and the halides of each of them. So let's take a couple of slides to do that here with the D block, the transition metals. So we've already seen that from scandium to manganese, the maximum oxidation state is possible, and this is possible with oxides as well. So we've got Sc2O3, TiO2, so titania, and here we've got the +4 oxidation state, +5, +6, +7. And these oxides are increasingly more oxidizing. So an oxide with the higher oxidation state is more oxidizing than one with a lower one. And there's a YouTube video here of some American kid making the manganese heptaoxide, which is a super strong oxidizing agent, and he chucks a load of random things I think he's got lying around the house in it and watches them burn. Very entertaining. It shows the oxidizing power of the chemical really well. I just don't think he's a very good chemist, to be honest. Certainly doesn't seem so safe. Now there are two more interesting things actually. So the first is that for a given element, the oxides get more basic as the oxidation state decreases. So for example, with vanadium, we've got 4 oxides with various oxidation states here. The top 2 are amphoteric oxides, whereas these 2 are basic. The same with chromium, so like at the top, this is more acidic, and they become more basic as we go down. And the final one is final thing to note, I should say, is that manganese, iron, and cobalt can make what's called mixed oxidation state metals. So, for example, the iron Fe3O4 can instead be written like Fe2 Fe3 to highlight the fact that one of the 3 iron atoms is in the 2+ oxidation state and 2 of the iron atoms are in the 3+ oxidation state. So these mixed oxidation state metal oxides are possible for, as I said, manganese, iron and cobalt. Moving on to the halides, I've got a diagram here of the first row of the transition metals again, with some of the fluorides and chloride compounds they can make. Now the ones highlighted in blue are the most stable oxidation states formed by the fluoride, and the ones in pink are the most stable formed by the chloride. So one thing we can notice in the first bullet point is that fluorine is better at stabilizing a high oxidation state compared to chlorine. Now we've got some evidence for this highlighted in these red boxes. So for example, vanadium can make a pentafluoride, and so can chromium, but there isn't a chlorine equivalent of these, so you can't get VCl5 and CrCl5. And the same with manganese and nickel, so these can have a tetrafluoride but not a tetrachloride. So this is good evidence that they're more stable with fluorine than chlorine. And actually the reason for this is very similar to what we were looking at with the group 15 halides in the P block videos. So it's actually one of the questions we looked at, why nickel could make NCl3 but chlorine couldn't make PCl3. So you can actually use those same sort of diagrams to show that. One other thing to note is that although fluorine is more oxidizing than oxygen, and with the oxides we could get the highest oxidation state of manganese, we can't get a fluorine equivalent of that. So there's no MnF7. And this is because of what's called steric crowding. So the manganese is a really small cation. Mn7+ is pretty small. And to cram 7 fluorines around one of those, especially with how many lone pairs fluorine has, there's just not enough room, especially with the electron-electron repulsions that will be present. It's just not possible. Now for one other nice little relation to my research that I've done before, you can see that iron is super happy to be in whatever sort of fluoride or chloride it's got. Is most they're all classed as most stable. And from a practical side of point of view, this is really interesting, because at some point in my PhD I really wanted to make these metal nanoparticles, so like little balls with platinum in the middle and iron around it. And I wanted to do this by adding platinum and iron to a solution and then adding a reducing agent, and having the platinum reduce first and then the iron reducing around it. It's quite a common technique that's been used for other things before. Now for this you need to make sure the reduction potential is the right way around. And if you use Fe3+, so having FeCl3 as the iron source, then the Fe3+ reduces before the platinum, so this wasn't possible. It's only possible with the FeCl2 because iron 2+ will reduce after the platinum, whereas iron 3+ will reduce before. So these oxidation states, and they really can make a difference to the way you'd do experiments in the real world. Now one final point that links nicely actually to the last video of the P-block lectures is how higher oxidation states are stabilized moving down the group. So the example I've got here is from the nickel triad. Now at the top of the group, nickel forms a fluoride NiF4, and in this case nickel's got the +4 oxidation state. But as we go down the group with platinum, we can actually form a hexafluoride, so platinum in the +6 oxidation state. And this just isn't possible with nickel. So this is because higher oxidation states are stabilized further down the group. Now this platinum hexafluoride is a very strong oxidizer and has a nice little bit of history. So it's actually such a strong oxidizer that it can oxidize oxygen. So O2 molecules can actually become O2 cations, which is very rarely done. Now the chemist that did this realized that the ionization energy of O2, so to make O2 into a cation, is really similar to the ionization energy of xenon. And at that point, the noble gases were thought to be completely inert. So then it was actually this chemist that was like, hang on, if I can oxidize oxygen with platinum hexafluoride, maybe I can do the same to xenon. And he chucked them together and it did actually work. So it was using this platinum hexafluoride as an oxidizing agent that xenon was first shown to be not inert in 1962.